Hi, welcome to 383 Complex Analysis, and this is lecture 18. So what I want to do today is I want to start the conversations on the Riemann mapping theorem. So depending on how much detail we want to get into, this can go from something on the order of a day or two lecture to something that is going to take 2 weeks. And so I would probably do more the 2 to 3 day lecture version of it, and use this as an opportunity to review some results you should have hopefully seen in real analysis. And if not, this will be a chance to at least talk about them and why we need all these techniques. So we'll obviously state the Riemann mapping theorem. Did I say Riemann hypothesis earlier? Or did I say Riemann mapping theorem?
Riemann mapping.
Okay, I wasn't sure if I've been primed by the conversation before class about the Riemann hypothesis to now promising proof of the Riemann hypothesis. We will do a proof of the Riemann mapping theorem. We will use results from both analysis and complex analysis. And we will finally come up with a situation where there are some results that are just true in general, that are just true about convergence in general. But when you apply them to sequences of real analytic functions, it's different than if you apply them to sequences of holomorphic functions. So whenever you see that, you should immediately be thinking, what is different in the complex case? What do we have that we don't have in the real case? So anybody want to hazard a guess? We still have a triangular inequality in the real case. I'm sorry? We have an ordering in the real numbers that we don't have in the complex. But if I give you a complex holomorphic function, what do we know about it that we don't know about a real analytic function? We do know it's infinitely differentiable, but if I tell you it's real analytic, we know it's infinitely differentiable. So, but if it's real analytic, it has a Taylor series. We do know open mapping, but there is something, and again, today is all about Riemann, but we are keeping track, and who are we forgetting? So there are the Cauchy Riemann identities, which lead to what? What is true about a complex differentiable function holomorphic that's not true about a real function? You know some physics. What about the closed integral? All right, certain closed integrals equal to 0, but related, you can actually express the value of your function by doing a closed integral of like f of zeta over zeta minus c along the boundary. You can represent any value as an integral of your function along a certain curve. That is the key difference between real and complex functions. And so again, you really want to just keep in mind, what do I have in complex that I don't have in real, to try to figure out how should we prove these results. All right, so this is a lot of stuff to get through today. And so I have just taken snapshots to save a little bit of time. So the first is the statement of the Riemann mapping theorem. So we have some omega, simply connected, open, and proper. So what does proper mean? Not all of complex plane, not the entire complex plane. If there's some point z0 in omega, there's a unique conformal map from omega to d that sends z0 to 0 and has f prime of z0 greater than 0. So this is essentially a normalization. We know that the derivative is not going to be 0. We proved that yesterday. And then this is just rescaling it so that it's now positive, just rotating it a little bit. So as a nice corollary, any two proper simply connected open subsets of C are conformally equivalent. I can map one to the disk, I can map the other to the disk, and therefore by flipping the map, I can map one to the other by passing through the disk. For those of you who know, your computer history, IBM in the beginning was the behemoth powerhouse, and all the different computer companies had their own language, but everybody had to be able to speak IBM. And so sometimes you would have two different competing companies, and the best way for them to communicate is each one would just talk to the other in IBM because they wouldn't know each other's language, and they would just pass through that. So you want to try to get a sense of which sets could possibly be conformally equivalent to the unit disk. We know it can't be the entire complex plane. Why not? So why can't the entire complex plane be conformally equivalent to the unit disk?
We need an extra point for that because we have non-compact versus compact.
Okay, so one thing is the image of a compact set compact? Not necessarily, because the the unit disk can be mapped to the upper half plane, and you can extend to be mapped from the boundary to the boundary. So this is a really good long answer, because you want to try to get a sense of which things stay and which things are lost in the limit. So maybe f of compact is not necessarily compact. So why can't we map the entire complex plane to the unit disk? Yes. Liouville, right? Liouville says if you have an entire function that's bounded, then it's constant. Well, if I'm mapping it to the unit disk, it's bounded in absolute value by 1. So the reason we have proper is Liouville. If f from C to D, bounded, then f is constant. Okay, so here's a couple of things to think about. Must f of an open set, again, f is always going to be holomorphic. Must f of an open set be open? Yes, this is in fact the open mapping theorem. So again, huge difference between complex analysis and real analysis. And then the others, so we may not be able to keep compact. So f of compact is not always compact. But f of connected will be connected, f of simply connected will be simply connected. And then the more interesting one, genus G. So let's say I have something over here that's has a hole in it. If I try to map that to the unit disk, they have very different topologies. They have very different structure. One of them has a hole. And the real reason for trouble, taking some kind of curve here, which then would become a closed curve over there, and just trying to look and see what would happen. And we'll be able to get a contradiction from something like that. Okay, so we want to talk about automorphisms to the unit disk. Well, if I have some set here, let's call it omega 1, and another set omega 2, and let's say f is an automorphism of omega 1, and let's say g is an automorphism of omega 2, and let's say I have my function h, which is my conformal isomorphism between the two. So if I have a function in automorphism of omega 1, I can make that a function on omega 2 by looking at f composed with h composed with h inverse. That will now map us from omega 2 to omega 2. Yes, did I do it the wrong way? Oh no, I think, wait, did I do it the wrong way? Yes, I want to do h inverse. And so now h inverse starts off with something in omega 2. I apply f, and then I apply h inverse back. Yes. Well, that's the whole thing that I'm about to ask, right? Is and we could of course go the other way. Given some g, I can write it in this form. Yes.
Sorry, I have a question for you. But when we're talking about like simply connected, is this only for f which satisfy which are conformal mapping?
Right. So for instance, we'll take a a conformal map.
Okay, because otherwise we do something, right? Yeah. Like then you just talk about it, like
All of C,
plane, right?
right. And so we're going to be having your function which is 1-to-1 and on to. Yep. So here is a way to just get an equivalence going back and forth between the two. So you give me any automorphism in one, and I can pull it back to the other. Or I can push it forward. So what this really tells me is I only need to understand the automorphisms in one set to understand the automorphisms in anything that's equivalent. So if I know the automorphisms of the unit disk, and I want to understand the automorphisms in the upper half plane, what I do is I take something in the upper half plane, and I map the upper half plane to the unit disk, then take one of my automorphisms there, and then I map back. And that will now give me an automorphism in the unit disk. I mean, in the upper half plane. So I will leave that as a calculation for you to do, is just take an arbitrary G in omega 2. And then if you pull it back, if I look at H inverse composed with G composed with H, that's now an automorphism in omega 1. So that now lives somewhere in omega 1. So I'll leave this as a calculation for you to do, to see that if you know the automorphisms in 1, you can pull them back and forth by using this function H. So unfortunately, for a lot of these calculations, you just have to sit with a piece of paper for a while and just go through the matchings and see that you can convert from one to the other. If you have trouble doing that, let me know. I'm happy to go into greater detail. But you just have to go through and just do the calculation and say, well, if I pull it back now, I know it lives in an automorphism of omega 1. So there has to be some F that this is equal to. And then that will finish the proof. All right, so now we have a slew of definitions to go through. And this is where it's really advantageous to have read the material beforehand. So the first is what it means to be normal. So what we're going to do is we're going to take an open subset of C, which we always call omega, and then we're going to be looking at a family of holomorphic functions. So why do you think we call it script F? Family, right? So family, omega is said to be normal if every sequence in F has a subsequence that converges uniformly on every compact subset of omega. Now, what's interesting is the limit need not be in F. It just has to converge. And we've seen situations where things can converge, but don't necessarily converge in the space. You know, if I have an open disk, I could have a sequence of points that are converging towards the boundary, and it converges, but it doesn't necessarily converge to something in the space. If I then want to use something like the accumulation theorem, which is, as you've learned by now, one of my favorite results to use in this class, well, I'm out of luck if it doesn't converge to something in the space. So the definition of normal is just that I have a sequence of functions that converges uniformly on every compact subset. So we can try to come up with examples of functions that would be normal. So let's consider Fn of x. So what we want now is we want a sequence of functions, holomorphic, and then we want it to converge. So one possibility is, let's say I give you the function z plus z squared, 1 over n, 1 minus 1 over n. Oh, sorry, z, yes. So what do you think about this? Yes. Well, let's take n equal 1. Okay. So, f of 0 of z is z. As n goes to infinity, fn of z goes to z squared. So would this be a good example of a normal family? Oh, yes, after I just said that, yes. F1 of z.
What does it mean for converge? It doesn't converge on every compact subspace, right?
Yes.
What is our omega here? The whole.
Well, but again, it doesn't matter, because if I take any compact subspace, the function 1 over z plus 1 over 1 minus z squared on a compact set, it's not going to deviate that much once it gets very, very large. Z is going to be bounded. And so we have to be extremely careful where we're looking. If I'm looking at the entire complex plane all at once, so this goes back to a lot of results from real analysis on uniform continuity. So this was uniform continuity covered. I'm seeing some people say yes and some people say no. How many people did uniform continuity? How many people did not do uniform continuity? How many people don't remember? Okay, if you didn't do uniform continuity, please let me know what book you used. I'm just curious in seeing, and if you did uniform continuity, let me know what book you used. I'm just curious to see what's being covered and what's not being covered. Right, but you should then go back tonight and look at uniform continuity. So continuity, for all epsilon greater than 0, there exists a delta such that for all xy such that x minus y is less than delta, then f of x minus f of y is less than epsilon. So this is uniform continuity. Given any epsilon, I can find a delta such that whenever x and y are within delta, then f of x minus f of y is within epsilon. This is a little bit different than continuity. Yeah.
Otherwise, it looks like given a positive epsilon, there is some delta that exists.
Right. You give me a tolerance. I want to be within 1/1000, and I can always find a delta such that if I'm sufficiently close, this is true. It always begins with for all epsilon. And that's how it starts. It's you give me a tolerance. I want to be within a certain level. Where would you want to put the for all epsilon?
Up there.
At the very end?
Yeah. Basically, the whole every epsilon.
Well, but this delta, note, delta is a function of epsilon. So this is one of the big peeves I have with the way a lot of math is written, is they hide the dependence. When you say for all epsilon, there exists a delta. Delta is allowed to depend on epsilon. So the standard definition of continuity at x is for all epsilon greater than 0, there exists a delta, which is a function of x and epsilon, such that for all y with x minus y less than delta, then f of x minus f of y is less than epsilon. And so here the delta is allowed to depend not just on epsilon, but on the point x. So depending on where you are, how close you have to be can change. Uniform continuity is there is one delta that works for given tolerance. You tell me how close you want to be, and I can find a delta that will always work. Okay. So a family is said to be uniformly bounded on compact subsets if exactly what you expect happens. You know, it's nice when we have, you know, the phrase tells you what's going on. You know, normal, I'm not quite sure what normal means. Normal means every sequence converges. Every sequence has a subsequence that converges. Oh, sure, that's normal, okay. Uniformly bounded, okay, that means, you know, you give me any compact set K, then for any F in the family, the absolute value of F of Z is less than equal to B. I don't like this notation. What don't I like about this notation? I want one of the letters to be a little bit more explicit. Yes.
You want to be sub K?
I want to be sub K. You know, to just really emphasize the fact that this bound depends on the compact set we choose. Let's take, for example, f of z equals e to the, let's do fnz is equal to e to the nz. Are these holomorphic functions? Yeah, these are very nice functions. Do you think they're uniformly bounded on compact sets? Could they be uniformly bounded on compact sets? So let's see. This is going to be e to the nx, e to the I and y. So the absolute value of Fn of z is going to be e to the nx. Yes.
You have omega, you said omega can get positive complex numbers functional parts. You're gonna have like Fn.
Right. So for instance, if omega is in here in the positive realm, the answer is a resounding no. But what if omega is entirely contained with real numbers that are negative? Will it then be uniformly bounded? Let's say your omega lives here. How large can the functions be in the omega on the left? Well, the absolute value is just e to the nx. N is a positive integer. X is a negative real. So what's the largest e to the nx could be? 1. So here, the answer would be yes. So not surprisingly, depending on what family I give you, the answer as to whether or not it's uniformly bounded on compact sets depends on where I consider my sets to live. So for this example, if I'm living in a realm where I have positive real components, it's clearly not going to be uniformly bounded. It's going to go up to infinity. If I, however, stay in negative land, then it will be uniformly bounded. And depending on what my compact set is, I can actually get better bounds. One of the things that I truly, truly love about analysis is frequently it doesn't matter. You just need a bound to exist. How many of you remember the proof of the fundamental theorem of calculus? Oh dear. Okay, we may have to prove that because you cannot graduate without knowing a proof of the fundamental theorem of calculus. When I used to recover from various things, surgeries, giving blood or whatnot, I would actually try to prove the fundamental theorem of calculus quickly. And if I had trouble, it meant I was not able to just leave yet and had to just wait a little bit until it was truly natural. You need to know how to prove the fundamental theorem of calculus. Okay, we don't have that many fundamental theorems. Is there at least one fundamental theorem you could prove right now if your life depended on it? Yes, which one? Algebra, right? In the complex analysis class, we proved the fundamental theorem of algebra. Okay, well, we should have an analysis proof in a complex class. Right? So one of the big things in the fundamental theorem of calculus is you have the upper sums and the lower sums, and you want to show they converge. And so what you often do is you show that you can bound the difference by some universal constant, depending on the function, divided by n. So as n goes to infinity, it goes to 0. What that means is you don't really care what that value of the universal constant is, because you're just taking the limit as n goes to infinity. It doesn't really matter what it is. Now, if you wanted to try to estimate the truth by using an upper or lower sum, then the value of that universal constant would matter in terms of how good of an estimate do you have. But if you're just trying to prove the fundamental theorem of calculus in the limit, doesn't matter. I just need some universal bound. So for a lot of these calculations, we don't necessarily need the best possible value. We just need to know that there is some constant that works. And so very rarely do we try to prove the best value. This propagates into writing papers. When you're writing papers, a lot of times you do not try to find the optimal constant. What you do is you try to find which number is the easiest number to write without making the paper an unreadable mess. So when Selbig was the first one to prove that a positive percent of zeros of the zeta function lie on the critical line, he did not try to optimize the argument and get the best percent possible. If his goal was a positive percent, he got it. Later, then people developed an industry of trying to get the best results there you could. All right. So the next one is a family is equicontinuous on a compact set K if for every epsilon greater than 0, there exists a delta greater than 0, such that whenever z and w are in K and they're within delta, then f of z minus f of w is less than epsilon. So I'm going to just paste in the definition we had earlier of uniform continuity. So here is the definition of uniform continuity. Does that look similar to the definition of uniform continuity? There's only one real difference. What's the difference? Yeah, one is for a function. So the difference is now for a family. So before, given epsilon, there exists a delta, which depends on epsilon and f, such that now, given epsilon, there exists a delta, which depends on epsilon and the family. So these are really strong conditions. You would say no matter what function you take in the family, I can find a delta that works simultaneously for all of them. So the question is whether or not we will be able to do stuff like this. But if we can, it's going to be wonderful because we have such uniformity as we move from example to example. All right, yes. Well, no, well, if it doesn't work for a couple of functions in your family, then it's not equicontinuous. So then you would have a new family. So if there's only finitely many exceptions, then you would just remove those exceptions. And then in what you have left over, it would be equicontinuous. Now, in some sense, what we really care about is, let's assume that our family is countable. Because if the family is not countable, well, but maybe we have an uncountable family. If we have a countable family and there's only finitely many exceptions, then we will eventually hit the last one and we'll be fine. So in the instances that we care about, if there's finitely many exceptions, you can just remove those from the family. If there are infinitely many exceptions, then it becomes more tricky. So you are right that we care really about what's going on in the limit, but the way the definition is worded, it has to be true for everything. Okay, so the big result is Montel's theorem, which I think interestingly, the book doesn't actually say Montel's theorem before it. It says it's the section on Montel's theorem, but I don't think it actually writes Montel right before it. So there's two parts to it. First, of course, we have the conditions. F is a family of holomorphic functions on omega that's uniformly bounded on compact subsets. Well, this is pretty standard. We're always working on open sets omega. We're always looking at holomorphic functions. The only real new bit is this assumption that they're uniformly bounded on compact sets. So you give me any compact set, and there's a limit to how large they can be. Okay? The first statement is F is equicontinuous on every compact subset of omega. And then the second is F is normal. So the difference is in the first case, we are going to be using some key results from complex analysis. In the second case, we are going to just be doing some general results in analysis, and it's going to be true in great generality. I'm not sure if we're going to get to the proof of part 2 today, because I really want to emphasize, based on some conversations here, on some analysis prereqs. So let's think a little bit about some examples. Let's do a real example. Let's do Fn of x is sine nx on, say, negative pi pi. Or if you want negative pi pi, if you want it to be an open set. Are these functions nice? Yes. Are they uniformly bounded? What are they uniformly bound by? Just by one. Right? When you talk about bounded, you always talk about the absolute value. Right? So if you want, you can say it lives between -1 and 1, which is essentially the same as saying its absolute value is 1. So do we think it's equicontinuous? So why not?
We're gonna
Yeah, so as n gets very, very large, they oscillate greatly. And so well, for any specific value of n, it's still going to be bounded. So let me shift to Mathematica. So let's define f xn sine nx. And I'd love to come in and manipulate. So let's plot f of xn. X goes from I minus, let's do 1 over n to pi. Let's have n go from 1 to 100. And so if you're looking at this, you can see the function really moving all over the place. So let's draw it over a larger region. Square root of it. So what should its value be at pi? Although, wait a minute, we've got to be careful. It should always be 0 at the limit, right? So let's go up to pi halves. And then let's do 2n plus 1. So what should I get there? So it should either be plus 1 or minus 1, right? So if I put in pi halves, maybe if I do this 4. I just want to have it as, or I want it to always be 1 at the endpoint at pi halves. I'm sorry. Oh, thank you. That's why things are going wrong. Thank you. There we go. Thank you. All right. I forgot to put in the floor function. Thank you. That's really why I was looking so strange. All right, so good. Now it's fixed, so it's always going to be 1. And what you can do is you can see that as we come in closer and closer and closer, we can have it oscillating more and more and more. So if we were to try to be equicontinuous, if I choose epsilon to be 1/2, I can eventually choose an n to be so large that the gap is going to be more than 1/2 for any delta you give me. And this is enough to show that there's an issue that it's not going to be equicontinuous. Yeah. I think I went back to the wrong one. They're right next to each other. So unfortunately, it is not equicontinuous. So this is a terrific example. And this just shows you that, yet again, the real and the complex cases are going to be fundamentally different. Okay, so what is different between the two cases? The difference is going to be the Cauchy integral formula. And before we use the Cauchy integral formula, what we're going to do is we're going to just talk about working with compact sets rather than working with open sets. And we want to work basically, if I have a point, everything about differentiability is a local phenomenon. So I can draw a small little ball about that point, and that's its own world. And what I want to do is I want to just make sure that I stay away from the boundaries so that I can stay inside my space. So you give me any point and I can draw something sufficiently small. So what we're going to do is this notion of exhaustion. Mathematical exhaustion is different than other types of exhaustion. So what we're going to do is the following. We're going to have a sequence of compact subsets of omega is an exhaustion if each one is contained in the interior of the next one. Any compact set is contained in one of these, and in particular, your set can be written as a union. So for example, the simplest way to prove that I have an exhaustion, let's say I have some set omega here. What I can do is I can draw, let me draw a simple set that's going to be easier for me to work with. You know, like an oval or whatnot. What I can do is I can first draw K1, and these will be all points that are 1 unit from the boundary. And then the next one I can draw would be K2, which would be all points that are 1/2 of a unit from the boundary. And then I can draw K3. This is hard to see over in black, which is 1/3, and this will be K3. So basically, you know, Kn will be the set of all z in omega such that the distance from z to the boundary of omega is greater than or equal to 1/n. Now, there's only one problem with this. You know, what if my set is infinite? So this is assuming omega is compact, or at least bounded. So if it's bounded, you know, what I can do is I can just take all the points that aren't too close to the boundary. And as I let my closeness get smaller and smaller and smaller, I'm going to be expanding upwards and getting the whole thing. So if you're not bounded, let omega n equal omega intersect the ball about the origin of radius n. And then let Kn be the set of all z in omega n such that the distance from z to the boundary of omega n is greater than or equal to 1/n. So if I do something like that, what I can basically do is I can just keep drawing giant balls and just only look at the part of omega that's within n units of the origin. And then as n gets larger and larger and larger, this is going to expand and cover. But at any moment in time, I'm always going to have just a finite amount. So the whole point of this is that I can try to reduce my calculations to looking at compact sets and then try to understand my set as a limit of compact sets. So I'm trying to approximate my general omega with a sequence of compact sets. Where have we seen this somewhat before? Let's see, if you go back to, it's normal if every sequence converges uniformly on every compact subset. So you're talking about what's going on a compact subset. We want to have conditions where things are nice and we can do whatever we want to do. Compact sets are really nice for stuff like that. Okay, so for Montel's theorem, again, we want a family of holomorphic functions. We want it to be equicontinuous, and we want it to be a normal family. And we've seen that equicontinuity can fail if we just look at nice real functions. So somehow we have to use something about complex. So let's just focus on the first part. The statement that we have a holomorphic sequence of functions uniformly bounded on compact sets, then f is equicontinuous on every compact set. And the big thing we have is the Cauchy integral formula. And so it says f of z minus f of w is 1/2 pi I integral over some curve gamma of f of zeta 1/zeta minus z minus 1/zeta minus w. We're using the fact that we can represent our function as an integral. So this is fundamentally different from real analysis. We do not have this in real analysis. So here, what we're going to do is we're going to take circles of radius, r, 2r, and 3r. And then here outside is omega. So what we're doing is we're choosing r so small that about whatever point we're centering ourselves at, say z0, that even if we draw a circle of radius 3r about z0, we're still entirely contained in omega. Or instead of looking at omega, we're trying to do things on compact sets. So maybe instead of omega, maybe what we're really looking at is some compact set K. And so here would be some compact set K, and we choose so small that we're entirely contained in K. All right. So now let's try to understand, and I think there might be a typo in the book. We want to understand, what can we say about this integral? If it's supposed to be equicontinuous, what that means is given an epsilon, we can find a delta such that this integral is small, right? So given epsilon, find delta, which is a function of epsilon, such that integral is small. Okay. Well, if we look at 1 over zeta minus z over 1 minus zeta minus w, if we just do a little bit of algebra, we're going to get a z minus w, and we're going to get a zeta minus z, zeta minus w. But what can you tell me about zeta minus z? So we're going to have gamma be this circle of radius 2r. And we're going to have z and w living inside here. So z and w are within r of each other. Or maybe let's see, maybe I'll have the circle centered at z. So we want it to be, so whenever z and w are within, let's see if this works. What can you tell me about zeta minus z? How big? Zeta minus z has to be at least r, because z is inside the first circle, zeta is on the second circle. What about, well, because if I have, for instance, z right here, yep. Let me keep this as, I'm trying to remember if I want to, do I want to have this centered at z? Right, I just want to make sure, do I want it centered at z? Yeah, let's keep it centered at z. So again, the worst, you could have it as 2r, but having it as r is fine. What about zeta minus w? That's also going to be at least r. But how far apart could zeta minus w be? I mean, could z minus w be? I'm sorry? Right, so we want w to be within delta of z. This is by assumption, right? So by assumption, z minus w will be less than delta. And so the absolute value of f of z minus f of w will be less than or equal to delta over 2 pi. What's the length of the blue curve? 2 pi r, and r is, the radius is 2r. then we have the function f of zeta, but f of zeta is bounded. So we'll put in the bound of f of zeta on the circle of radius 2r. And then we divide by the zeta minus z, zeta minus w, which is an r squared. I'm sorry? Nope, because I'm doing the absolute value. So if I look at how large this integral is, well, we had in the denominator, 1 over zeta minus z minus 1 over zeta minus w was z minus w over zeta minus z, zeta minus w. And because zeta minus z and zeta minus w are at least r, then their product is at least r squared. So 1 over that is going to be less than 1 over r squared. So now all we need to do is we want this to be less than epsilon. So if delta is less than epsilon, the 2 pi's cancel, 1 of the r's cancel. Let's do 2, I think. We want this to be less than epsilon. So it would be epsilon over 2b2r plus 1 will be fine. Because if you now put that value in for a delta, then the above expression will be less than epsilon. Oh yes, and an R in the numerator. So now we have to be careful. Are we allowed to put ourselves an R there? I'm sorry? Well, no, but the bound just depends on the disk of radius 2r. It's still a universal. It is depending on r, but it's for this compact set that we're looking at. So because it's equicontinuous, so in fact, instead of using b2r, because we live on k, I could actually replace it. So that is a good point. So what should we replace this with? Just bk. No, we're saying it's uniformly bounded. I'm sorry, it's uniformly bounded on compact sets. So since it's uniformly bounded on k. So I can replace the b2r with a bk. I do have it is bounded by b2r, but I don't want to use b2r because that depends. I want to have something that's completely independent. So the only thing that's now slightly problematic is we have an r. And so we want delta to be small relative to this. So what could we do? Well, but we have drawn a circle. Yeah, we want z minus w to be less than delta. So what do we know about r relative to delta? R is greater than delta. So we have this. We know R is greater than delta, right? So if delta is less than epsilon delta over 2 bk plus 1, we should be okay. Ah, 2r is greater, okay. So that implies R is greater than delta over 2. So if we take delta to be less than epsilon delta over 2 bk plus 1, that will be less than epsilon r over 2 bk plus 1. Right, so then the question is, Let me just stop over here. Let me just take a quick look. If not, I'm probably going to just have to write this up and send this. This is the part where we've got to be very careful about tracing everything. So at the end of the day, we have our yeah, let me pause it here because it's already 11:51. So I will pause this and then just write this up and send that. All right, sorry about that.